Now we will take a look at ionic crystals. In ionic crystals we have a positively charged ion and negatively charged ion which attract each other. That's due to Coulombic or electrostatic forces. So we actually have an electron donor and an electron acceptor, so we have complete ionization and the electrostatic forces between the two ions holding the crystal together. So let's consider sodium chloride example. In sodium atom electron configuration, we have 1s2, 2s2, 2p6, 3s1. So sodium has one valence electron and it has a low electronegativity. Because it has a low electronegativity, it's going to lose this electron and release it to the lattice and become positively charged. So we obtain a sodium plus ion. Chlorine atom, on the other hand, has 1s2, 2s2, 2p6, 3s2, 3p5. So the valence electrons are, there are basically 7 valence electrons, but we have one missing to complete the outer shell. Therefore it has a high electronegativity, so it's going to basically accept the electron that sodium has provided, so it gains an electron and becomes negatively charged. So we can summarize this as follows. Sodium will absorb 5.1 electron volts. That's called the ionization energy, because it's the first electron that it is releasing. It's the first ionization energy, but anyway, so that is what we need. And so we obtain sodium plus ion and an electron. Now this electron is accepted by chlorine, so chlorine becomes negatively charged, chlorine minus, and in the process we release 3.6 electron volts. That's called electron affinity. So that is the amount of energy released when an atom absorbs an electron. On the other hand, we can look at this process between sodium plus and chlorine minus to form the sodium chloride structure. Sodium plus and chlorine minus will form sodium chloride compound, and 7.9 electron volts electrostatic energy is released in the process. And we can summarize the overall reaction as sodium, neutral sodium and chlorine come together to form sodium chloride with the net energy released 6.4 electron volts. That's the cohesive energy. So as you can see, cohesive energy is ionization energy minus electron affinity minus electrostatic energy. So 5.1 minus 3.6 minus 7.9, it's minus 6.4 electron volts per atom. That is the energy that we released. So this results in a face-centered cubic structure. That's what we call sodium chloride structure. We have alternating sodium and chlorine atoms. So in each sodium plus ion we have 6 chlorine minus ions that is surrounding it. And that basically summarizes what's going on in sodium chloride. Now, if you look at the interaction between ions I and J, so in this crystal structure, we call this Uij. So Ui, that is all interactions of the ith atom, will consist of some of the interaction potentials with the jth atom, and where J is not equal to I. So Uij is equal to minus q squared over rij. So we have a positive and negative charge that is interacting, let's say, so then this would be minus q squared. So this rij will introduce a sign here, you can guess, because it depends on the interactions between positive positive or positive negative or negative negative ions. And we have a plus repulsive potential, that is our Pauli exclusion principle, that is due to the fact that two electrons cannot occupy the same orbital with the same spin. So this equation, we don't have kq squared over r here, so this is written in CGS. And here when we do this, the electrons form a closed shell. When the sodium provides its electron, chlorine accepts its electron, we have a full shell electronic distribution, so it is symmetric. Now, the core repulsion, Pauli exclusion principle, we can take empirically as lambda times e to the minus Rij over rho. So lambda and rho are some constants, so this is exponentially increasing as the atoms approach each other. So Rij is some multiple of the distance between nearest neighbors. So nearest neighbor distance we call capital R, and we have a reference atom I and atom J that are at a distance Rij, so the total distance between them is some multiple of the nearest neighbor distance in the crystal structure. Now the total energy of the crystal will be sum over I and J, so we go through all atoms and find their pair potentials and add them up, but we will be double counting in that case, so we have to divide it by 2, or it's the number of atoms and multiplied by the potential energy of the ith atom. So this would be capital N times sum over J lambda e to the minus Rij over rho. So this is our repulsive part, Pauli exclusion, and this is our electrostatic energy, and that is plus or minus q square over Rij. Sign will be determined by the charges. So, and capital N is number of atoms. Now, if we assume for simplicity that the repulsive interaction is non-zero only for nearest neighbors, then we can introduce this Z, the coordination number, which is the number of nearest neighbors. So the repulsive interaction, the Pauli exclusion principle, is only effective for nearest neighbors, so we will have Z lambda e to the minus R over rho, so only for the nearest neighbors. And then we have minus alpha q squared over capital R, nearest neighbor distance capital R. So we have introduced this constant alpha here, which is called the Medline Constant, and we have to evaluate this. So we have to add up the contribution from each atom, so we multiply with and to obtain the total energy of the crystal. So this alpha is sum over I not equal to J minus plus 1 over Pij, and where Pij is given by Rij, the distance between ith and jth atom, is Pij multiple of the nearest neighbor distance. Now notice here I have introduced this as minus plus. That is due to the fact that I have this minus sign here. So I have defined alpha such that I'm going to have a minus sign here. So in order to do that, I have to basically consider a positive contribution would be due to two same charges. So I have to introduce a minus sign in the alpha so that the contribution would be positive for two positive charges. So you can see that instead of having plus minus 1, I have minus plus 1. So anyway, so you can consider the interaction as it is. You can calculate the potential energy, but then multiply it by minus 1 to get the alpha Medline constant. So here's an example for a one-dimensional chain of ions. We have positive, negative charges. The nearest neighbor distance is capital R. Now, when I calculate for the ith atom, the potential energy plus minus q square over Rij plus a repulsive potential. So for like charges, we have a positive energy. For opposite charges, we have negative energy because it's attractive. So Uij is minus q square over Ri1. So if I call this atom the ith atom, this is the first, this is the second, this is the third, etc. So then I will have minus q square over Ri1 plus q square over Ri2 minus q square over Ri3, the distance between ith and the third atom, etc. So the total interactions involving the ith atom will be the sum of Uij for I not equal to j, plus, if I'm assuming only interactions with the nearest neighbors that's contributing to the repulsive potential, coordination number times lambda e to the minus capital R over rho. So Then I have this term sum over j plus or minus q square over rij. So in q square parentheses sum over j plus or minus over rij. So remember this, I introduced this minus alpha here, which made this minus plus in the alpha definition. So let's evaluate this plus or minus 1 over rij. So I look at this atom. The distance between the ith atom and the first atom is r. So first term will be minus q square over r. So then I will have minus 1 over r here. That would be the first term. But because I have two nearest neighbors, so I have to consider not only this one, but also there will be another one here, which is 1 prime, let's say, that will give me the same contribution. So I have to multiply it by 2. So 2 times minus 1 over r. And for the second atom, I see it's going to be plus q square over 2r and plus q square over 2r. So plus 1 over 2r. And then again, I have two nearest neighbors. So it will be plus 1 over 2r. And then for the third one, I have the distance becoming 3r. So that is this distance here is now 3r, and I will see that this will be the same charge plus q minus q square over 3r, because it's attractive, minus 1 over 3r, and again multiplied by 2 because I will have the mirror image on the other side, etc. So this goes on like this. And in order to evaluate this sum, I consider natural logarithm of 1 plus x for x close to 0. You can see that this Taylor series expansion will give me, for x equals 0, natural logarithm of 1 plus the derivative 1 over 1 plus x times x minus 0. X evaluated at x equals 0, this gives me just x. And then I have minus 1 over 2 factorial 1 over 1 plus x squared. That's the minus sign comes from the second derivative. Evaluated at x equals 0, x squared, etc. So you can see that this is x minus x squared over 2 plus x cubed over 3 minus x to 4 over 4, etc. So this sum can be written as sum over n equals 1 to infinity minus 1 to the power n, capital N minus 1, x to the n over n. For n equals 1, for example, we would obtain minus 1 to 0, which is 1, x to 1 divided by 1, the first term, x. For n equals 2, I would have 2 minus 1 to 1, that will give me a minus sign, x squared over 2, etc. So this continues like this. So therefore, I see that if I were to set x equals to 1 in this summation, I would obtain for sum over j plus or minus rij, if I take this into minus 2 over r parentheses, I will obtain 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, which is basically what I see in natural logarithm of 1 plus x Taylor series expansion. So this is approximately minus 2 natural logarithm 1 plus 1 divided by r, which is minus 2 log 2 divided by r. Again, notice this minus sign here, but because of the definition of the Medline constant alpha, I need to change that sign to plus. So it's plus 2 natural logarithm 2 for a one-dimensional change. So this is an approximate result for the Medline constant. So you can see here, because of this minus sign that I have introduced, minus alpha q squared over r, I changed the interaction sign from plus minus to minus plus, and therefore the answer I obtained, minus 2 log 2 over r, is actually becoming plus 2 log 2 for alpha for the one-dimensional chain. Now, as a further example, let's consider the sodium chloride crystal. So I look at one sodium plus ion, so that is the one right in the middle. So it has 6 nearest neighbor chlorine atoms. So you can see I have labeled them 1, 2, 3, 4, 5, and 6. So those are the chlorine atoms at the face centers on each face of this cube. So those are at a distance a over 2. And then I have 12 sodium plus atoms at a distance r square root 2. So you can count those atoms. Those are the sodium plus atoms. So we will have one, 2, 3, 4. Those are the ones that are on the same plane with the sodium plus. That's the middle plane of this cube. And then I have 5, 6, 7, 8. That is another middle plane. And then I have 9, 10, 11, 12. And those are basically the ones that are at a different plane. So that would be this plane here. So you can see that these ones will be also on the same plane with the middle sodium plus ion. So those are at a distance capital R square root 2. So that's a over 2 root 2, which is capital R square root 2. And then I have for the so nearest neighbor, first nearest neighbor, second nearest neighbor, third nearest neighbor, 8 chlorine minus ions. Those are the chlorine minus ions that are at the corners of this cube. So there's 8 corners. So we have 8 chlorine minus. And those are at a distance basically a root 3 over 2. So they are at a distance capital R square root 3. Okay, so the total attractive Coulomb energy we can write as minus Q square over R multiplied by 6. So between chlorine atoms and sodium atoms, we have Q square over R, but with a minus sign because it's an attractive. One has positive charge, one has negative charge, and we have 6 of them. And then we have for sodium, the 12 sodium plus ions and the sodium plus in the middle, we have 12 of those, and the distance is capital R square root 2, so it will be plus Q square over R square root 2 multiplied by 12, and then from the 8 chlorine atoms we have minus 8 Q square over R square root 3, etc. So just this sum from the 3 nearest neighbors that are within this 1 unit cell gives me a factor 1.46. Because I have introduced this minus sign here, what I have in parentheses is the Medline constant. So that is 1.46 from 1 cells. If you were to calculate it from all cells, you will obtain 1.75. So that's already quite close to the correct answer. So we see that this alpha is a geometry dependent factor, and for the total energy, the Lennard-Jones potential, we have capital N number of atoms, Z lambda e to the minus R over rho, assuming Pauli exclusion principle applying to only nearest neighbors with the Z coordination number, minus Q square alpha over R. And we have evaluated this R, let's say. So to find the equilibrium distance R0 between atoms, I have to take its derivative with respect to R and evaluate it at 0. So the derivative will give me Z lambda minus 1 over rho e to the minus R over rho, and then minus the derivative of 1 over R will give me minus 1 over R squared Q square alpha equals to 0. So this will give me R0 squared e to the minus R0 rho equal to Q square alpha rho divided by Z lambda. So that's what I obtained from this equation. So this is satisfied by the equilibrium distance R0. So I can substitute for e to the minus R0 over rho Q square alpha rho divided by Z lambda R0 squared. That's what I do here. So Z lambda times Q square alpha rho over Z lambda R0 squared. Z lambdas cancel. And then I have minus Q square over alpha R0. And therefore, in minus alpha Q square capital N over R0 parentheses, I have 1 minus rho over R0 for the total energy. Now when R0 is A over 2, so going back to the sodium chloride crystal, 2.8 angstroms, alpha is 1.75, so this is once again sodium chloride structure. So this is for sodium chloride. And rho is 0.1 R0. We can obtain U0, the equilibrium potential energy, divided by the number of atoms to be minus 8 eV per atom. So this is our cohesive energy. So we find that the melting point of sodium chloride as compared to sodium metal is a lot higher, and it's also bulk modulus is a lot higher. Therefore, the ionic bond is very, very strong. We will talk about the metallic bond later on. Now, so what have we done here? We talked about the ionic bond. Ionic bond will occur if one atom has low electronegativity, one atom has high electronegativity. Low electronegativity atom will be donating its electron, high electronegativity atom will be accepting it to form a closed shell structure, and the resulting ions will have Coulombic forces developing between them that holds the crystal together. The energy required to ionize the atom is the ionization energy. The energy released in the process of accepting the electron is electron affinity, and the energy released when we form the sodium chloride structure between the two ions is electrostatic energy. Total energy that is being released to form the sodium chloride crystal structure is the cohesive energy, 6.4 eV. That's the difference between ionization energy, electron affinity, and electrostatic energy. So we have talked about how to write this potential energy for a general ionic crystal. Well, we need to look at the interactions of the ith atom with the rest of the atoms, and we need to add contributions from all interactions of an atom and then add it for all atoms. So Uij is minus q square over Rij, where I and j atoms are interacting. Rij is the distance between them, and then we have the repulsive potential, and as a result of the ionization process we have obtained closed shell structures, where Rij was written in terms of a multiple of the nearest neighbor distance. So with that we have obtained for the total energy of the crystal number of atoms times energy per atom, and sum over, that is basically sum over j lambda e to the minus Rij over rho plus or minus q square over Rij, Pauli exclusion principle, repulsive potential plus the attractive and repulsive alternating electrostatic energy. So this will be, sign determined will be by charges, charge signs. Now for Pauli exclusion principle, we assume for simplicity that this is really only a strong interaction between nearest neighbors, so we just need to calculate the interaction between the ith atom and its nearest neighbors. The number of nearest neighbors is the coordination number z, so just multiply it by z lambda e to the minus r, the nearest neighbor distance, divided by rho, and we can write the second term as minus alpha q square over r, where we have introduced alpha, the Medline constant. And because of this minus sign, for two charges that have the same sign, we have plus q square over r energy, but the Medline constant becomes minus, so because we introduced this minus sign. And we have calculated the Medline constant for a one-dimensional chain, and using the series expansion, Taylor series expansion of natural logarithm 1 plus x around x equals 0, we found an approximate answer to be 2 log 2 for a one-dimensional chain. For the sodium chloride crystal, we have carefully examined the positions of the nearest neighbors, where we find that r root 2 and r root 3 are the nearest neighbor, second nearest neighbor, third nearest neighbor distances, and with that we can obtain the Medline constant contribution from one cell, and when we include the fourth nearest neighbor, fifth nearest neighbor, etc., we actually obtain 1.75. So this is basically quite close. And when we obtain the total energy of the crystal, if we take its derivative with respect to nearest neighbor distance and set it equal to the equilibrium nearest neighbor distance, this will be 0 when we have capital R is equal to R0. And with that, if we substitute what we obtain for e to the minus r0 over rho, we obtain the total energy in the equilibrium situation minus alpha q squared capital N over r0, 1 minus rho over r0. The energy of the crystal when it is in the equilibrium position is the cohesive energy. So that's basically what we obtain here. And if you substitute the numbers for sodium chloride, we obtain per atom minus 8 electron volts energy. The melting point of sodium chloride is 1100 degrees C, so we see that it's greater than the sodium metal 400 degrees C. So this is also the energy suggests minus 8 dB is quite large energy. It's quite a strong bond that we're forming in this ionic structure.